Alright, so we are going to go over how to draw Lewis dot structures. To do this, we're going to start with our finding our valence electrons. We have to look at our valence electrons on this. So let's review how to do that first. Whatever atom I'm looking for, so let's say I'm looking at phosphorus. All I'm going to do to determine their number of valence electrons, because remember, valence electrons are just in their outermost shell, how many electrons are in that outermost shell. We don't care about anything on the inside anymore, because they're not interacting with the world. We only are worried about what's outside that's hitting the next atom, or hitting the person, or hitting anything that's next to it. So we're going to look for phosphorus. We're going to say, okay, phosphorus is on this period, so we're going to go 1, 2, 3, 4, 5. So phosphorus has 5 valence electrons. The D block and the F block are very, very weird in how they work with this, so we are just going to pretend like they're not here. Alright, so that's where these 1A, 2A, 3A, 4A, 5A, 6A, 7A come in handy. That gives you the number of valence electrons. If I'm talking about tellurium, it has 6 valence electrons. Alright, so we are going to be using a Lewis dot structure here with that. So using that tellurium, I'm going to put in my electrons. I said I had 6 valence electrons, VE valence electrons. They can fit here on top, here on the side, here on the bottom, or here on the side, on the left side. And we're going to follow the same rules as we did with spin, that they cannot sit on each other's laps until they have everything else filled in. So 6 valence electrons, and it doesn't matter where you start. I start on the top, but it really doesn't matter. 1, 2, 3, 4, 5, 6. Alright, if I was talking about, what's another good element here? Let's go back. Let's talk about tin. Well, tin has 4 valence electrons. So again, I have my places that I can put it. I'm going to go 1, 2, 3, 4. Alright, well now how do we start putting these things together? Well, let's look at a compound, NH3. Alright, well, nitrogen we know has 5 valence electrons, so we put 1, 2, 3, 4, 5 valence electrons. Hydrogen has 1 valence electron. Alright, and so when I look at my atom here, I can see that it wants another electron here, it wants another electron here, and it wants another electron here. Well, I happen to have another electron, a second electron, and a third electron that would all fit. So I can redraw this like so. Alright, and this, everything has the electrons that they want to become like the noble gas in their period or the period before them. So everything's happy. So we know this molecule is stable. This is ammonia, by the way. We take that, we say N, and if we had a double electron like this that was shared by these 2 atoms, we can change it to just a dash. Alright, so this is how we would end up drawing it. I've also seen these drawn like this. Either way, I don't care. This is known as a bonding pair of electrons because it bonds that nitrogen and that hydrogen together. This is known as a lone pair because it is only on one lone atom, not 2. Alright, let's do one more really quickly, and then with a double bond, and then we'll call it good. So if I have something like this, if it's more complicated that I don't just have one central atom, I'm not sure which atom to start with, always start with the atom that wants the most bonds. Silicon has 4 valence electrons, wants 4 bonds. Hydrogen has 1 valence electron, wants 1 more to look like helium. Oxygen has 6 valence electrons and wants 2 bonds. So we're going to start with silicon. It wants the most bonds. 1, 2, 3, 4. Next we'll put on our oxygen, and the first thing that we're going to do is put it so that I can bond it. Okay, my first valence electron is going to go to bond these two atoms together. So 1, 2, 3, 4, 5, 6. Now I notice that I still need 1, 2, 3, 4 places on my atom filled, but I only have 2 atoms to fill them. If this is the case, we're going to cheat a little bit, and we're going to say we are going to have a double bond. Okay, so this oxygen and silicon are now going to share these 2 electrons to fill up their octet and these 2 electrons. So they're going to be sharing 4 electrons, or have 2 bonds between them. And then I'm just going to put my hydrogen here and my hydrogen here. So this would look like, remember to always keep your lone pairs like that. All right. There is a homework assignment on this, so make sure you grab it, practice up with it, and we'll see you next time.